The team has grown slightly since the introductory webinar a year ago. Several center postdocs and students have joined as tenured faculty around the US. The team consists of approximately 27 academic faculty, 11 NIST collaborators, and a large number of postdocs and students across numerous institutions. The center's external assessment panel provides the center researchers and NIST with written and verbal reporting related to the center's progress toward its year-end and its long-term goals. The EAP consists of a number of prominent individuals representing engineering, social science, economics, and public policy. The mission of the Center of Excellence is to support measurement science to enable researchers the ability to study and understand the underlying attributes and factors that make communities resilient to hazards. Ultimately, providing risk-informed decision support to community leadership and their constituencies to optimize a combination of public and private investment in resilience planning over time. The Center of Excellence activities focus on three key thrusts, namely thrust one, the development of the multidisciplinary computational environment known as INCORE. To accomplish this requires the collaboration of numerous disciplines and specialists, including structural and geotechnical engineering, coastal engineering, transportation engineering, risk analysis and operations research, economics, software architecture and database management, social sciences and post-disaster investigation and assessment, and interdependency and network analysis. Thrust 2 focuses on standardizing data ontologies, robust data architecture, and developing tools to support the computational environment. Thrust 3, the validation of the data collection process, including its integration into INCORE through Hindcasts and field studies. And so you may recall the webinar last year focused on Thrust 1. This year, we place equal focus on Thrust 1 and 3 with some information on Thrust 2. So there's a number of center research issues, and to highlight a few, the quantitative tools and metrics for assessing community resilience are in a rudimentary state or are even not available. And so this is one current research issue that the center focuses on. Multiple hazards, these are interconnected, interdependent systems, have to be considered. The consideration of uncertainty, both aleatory and epistemic, has to be included to make a fully risk-informed decision or support that decision. And then plans and guidance are needed, and that's perhaps at the year 5 point. And then existing and building and infrastructure systems, as well as new construction, both must be considered. And perhaps one of the most important is that code standards and regulatory documents must contain consistent performance goals and currently do not. So some other research and implementation questions that eventually will be answered or we seek to answer as a team. How can community leaders know how resilient their community is? How can they know if their decisions and investments to improve resilience are making a significant difference? And then how do they deal with the uncertainty and risk? How do they propagate that through the models, and how do they account for that in their decision-making process? So within Thrust 1, the development of INCORE, the team considers individual hazards, including hurricanes, tornadoes, earthquakes, and tsunamis, wildland and urban interface fires, and floods and storm surge. Hurricanes are treated as a multi-hazard problem with wind surge and waves all combined, and modeling coastal inundation, for example, modeling coastal inundation with a research-grade AdCirc mesh for use as input to INCORE. Physical infrastructure consists of building models developed based on principles of engineering and physics, fragilities for damage, loss, functionality, and restoration and recovery. Transportation networks are modeled with the ability to damage bridges, portions of roadways, and soon railway systems. Water systems and electrical power are modeled at the distribution level and can be coupled for dependency, as you'll hear about in the next portion of the webinar. Communication networks have been started and will be expanded upon over this year. Even during the proposal development stages, the team recognized that while physical infrastructure is critical for resilience, the metrics by which a community measures its resilience and recovery are rooted in social science and economics. Thus, there's a team of social scientists working to working on defining performance improvements in community resilience based on adoption and implementation of policies, codes, and standards. Key to this development of optimization strategies for enhancing this includes intelligent algorithms. In order to synthesize the interdisciplinary work being conducted within the Center of Excellence, 4 test beds are currently in progress. Centerville, which you'll hear about in quite a bit of detail shortly, the Seaside, Oregon test bed, the Memphis, Tennessee Metropolitan Statistical Area test bed, and the 4th and newest test bed is Galveston, Texas, including the Boulevard Peninsula, which enables the center researchers to study multiple hazards generated by a hurricane. Each of these test beds incorporates detailed social and economic network modeling to study mitigation strategies, recovery models over time following an event, and optimization in time and space for risk-informed decision support. Key to measuring community resilience is defining resilience metrics in terms of physical, social, and economic systems. General recovery is supported by recovery of physical systems such as time to functionality, but often measured in terms of social and economic factors or metrics. These are metrics such as retaining businesses and related employment, jobs, revenue, resources, change in income distribution, and percentage in poverty, but also considering the most basic and fundamental needs in life, such as survival and safety, food and water, and health. Developing a robust data architecture that allows data to be easily ingested into INCORE or data to be accessed across multiple discipline-specific databases is the focus of Thrust 2. This included NCSA identifying user requirements based on different data set types. For example, fragilities that are a function of more than one intensity measure. To be able to assign these requires building a taxonomy for all hazards, which you'll hear about more in the Joplin-Hindcast presentation later in this webcast. Incorporating key data types from economics and social science and the associated metadata, as well as management tools, is a necessity. Key to the development of the robust data architecture is the team's understanding that while we may develop new data types and tools, it's critical to include existing data and ontologies for full synthesis. Thrust 3 consists of validating the full architecture for INCORE, which is made up of tasks 1 and 2. This will be accomplished through a robust series of checks and hindcasts ranging from the single building or infrastructure component level, economic component, to single infrastructure sector validation. This will be done at points in time to validate damage modeling, loss estimation, and functionality and recovery models. The first such hindcast model, as I mentioned, is the 2011 Joplin tornado, which will be introduced by Dr. Terry McAllister shortly. As an example, consider the simplest wind field model for a tornado, shown in the bottom right of this slide. It is based on almost 40 years of tornado data and allows the analyst to model a tornado either with mean values or stochastically with multiple realizations in a community. For the tornado model, one question we seek to answer is, does such a model provide the necessary information for accurate community modeling to support risk-informed decision-making for planners and stakeholders? Validation at each step along the way allows the team to assess and compartmentalize or isolate modeling errors.
Several test beds have been initiated since the beginning of the center. The test beds have been designed to, 1, allow center research teams to initiate, test, and modify essential community resilient assessment models and algorithms before the INCORE platform becomes fully operational. 2, stress these assessment models in a controlled manner. 3, examine varying degrees of dependency between physical, social, and economic infrastructure systems. And 4, facilitate the interdisciplinary collaborations and approaches to community resilience assessment that will be essential for a center to achieve its ultimate goal.
Traditional engineering design approaches focus on performance of individual facilities under individual hazards through codes of practice primarily. The aftermath of recent extreme events has revealed the shortcomings of these traditional approaches. The Centerville Testbed was introduced early during the first year of the center's research program, and it had really two fundamental purposes. First of all, as Paula mentioned, to enable fundamental resilience assessment algorithms and databases to be developed in a preliminary form, coded and tested at an early stage before the more refined measurement methods and databases for physical, social, and economic systems had been fully developed and matured. And second, and equally important, it was devised to provide a structure for interdisciplinary teams to work together toward a common purpose from the beginning of the center, which is something that's been very, very difficult to achieve in past centers involving interdisciplinary research. The Centerville community is a typical middle-class community situated in the central part of the United States, and you'll learn a great deal more about it in the course of these presentations. I'll just give you a brief overview. The household income average is close to the national average. There are pockets of low to moderate income residents and vulnerable populations within the community. The economy is reasonably well diversified between the business, commercial, economic, and industrial, education, healthcare, and governmental sectors. The population of Centerville is approximately 50,000 people. There are approximately 20,000 households within the community. Of those, 20% are headed by somebody with a college degree. 20% are headed by somebody with less than a high school education. The median household income of about $52,000 is close to the national median. In terms of employment, approximately 32,000 residents in Centerville are employed. The majority are in the retail, services, government, and healthcare areas. In terms of building construction, the built environment of Centerville is modeled with four basic physical infrastructure systems and components: buildings, transportation, water, and electrical power. And we selected these four systems for two reasons. First of all, the fragility models were relatively mature at the time that we started doing the study, at least for the individual systems. And second, they represent distinct topologies. And third, the interdependencies between the water and the electrical power systems in particular could be examined in some detail at a very early stage in the center's research. This is a schematic of the transportation network within the system, within the city. The road network consists of highways, both primary, secondary, community roads. There are four bridges which separate the population centers, which are east of the river, from the major employers and the regional hospitals, on the regional hospital on the west side of the river. So this, having a virtual community like this, allows us to move the various components of the community around to determine what the impact of various configurations might be on its ability to withstand and recover from a disaster. The Centerville Water Network and the Electrical Power Network both follow the public right-of-way of the road network, and this is very common in urban areas. The Electrical Power Network is modeled at the generation, transmission, and distribution level, but it's not modeled at the individual building supply level. Centerville is susceptible to two primary natural hazards: earthquake and tornado. Last year we talked briefly about the tornado modeling. This year's presentations that you're going to hear in the following presentations focus more on the earthquake hazard. We imagined a magnitude, a 7-point earthquake with an epicenter of approximately 40 kilometers from the centroid of Centerville, in order to look at the impact of such a scenario event on the distributed infrastructure within the community itself. And so our presentations this morning will focus on losses due to that particular event. The social and economic metrics that we're considering as part of the study are five. I'll give a plug for the NIST-sponsored Center for Resilience, the Community Resilience Panel, which has tasks involved in looking at community resilience metrics. They've identified over 100 so far. We're focusing on 5 of these. They're very much dependent upon the community. These are metrics that I think everybody agrees are important in most communities, and so we selected those for that reason, to test our assessment and our decision algorithms. Note that those community metrics are community dependent, and actually most of them are actually based on social and economic factors, which means that the social and economic members of the team are actually, as I might say, driving the bus when it comes to determining the appropriate criteria which ultimately will be implemented to enhance community resilience. Thank you, Paula.
This framework includes the following components. We first start with a spatial and temporal hazard characterization at a community scale. And for Centerville, we focus on earthquake hazard. And then we move on to portfolio level damage assessment, followed by a functionality loss estimation. And that serves as a starting point of building portfolio recovery modeling. Ultimately, this quantitative assessment framework for building portfolios, together with those developed in other center tasks for different physical and socio-economic systems, will collectively form the basis for risk-informed decision to support community resilience planning. So in this study, we addressed the following challenges: uncertainty propagation and spatial correlation modeling from hazard characterization all the way to decision support. Building functionality assessment considering availability of utilities. Building portfolio recovery trajectory and recovery time estimation. And finally, we ensure scalability of our analysis algorithm as we move beyond Centerville to larger communities. This analysis framework resulted in 5 building portfolio performance metrics. Immediate occupancy ratio, the percentage of a building portfolio that can provide safe occupancy immediately following a disaster. Household dislocation ratio. This is estimated by a household dislocation algorithm developed by the center social team and using building damage estimation as one of the input. Direct loss ratio, the ratio of total direct loss to total assessed value of a building portfolio. And then portfolio recovery index, the percentage of buildings that are in any of the 5 predefined functionality states at any given time following a disaster. And finally, we have portfolio recovery time, the time takes for target percentage of buildings to regain or re-achieve their full functionality states. In this analysis, we estimated not only the mean, but also the uncertainty of all those 5 metrics. And the Centerville special issue, however, focused on the first 3, and which have been incorporated in the in-core alpha version that Dr. John Lee will demo later. So as introduced by Professor Bruce Ellingwood before, the Centerville test building portfolio include about 1,500 wood structures in 7 residential zones, 151 steel and reinforced concrete buildings in 2 retail and business zones, 70 steel buildings in 2 industrial zones, and about 19 reinforced concrete and masonry buildings for schools, hospitals, and fire stations. So we performed the damage assessment first to the Centerville building portfolio for the 7.8 earthquake scenario. We produced the damage, including the damage to structural components, non-structural acceleration sensitive, and drift sensitive components respectively. Those information was passed to the center economic team to forecast the economic impact to the local economy. Then through a damage to functionality mapping, we obtained the building functionality states immediately following the events, which is the starting point of the recovery. Following the Centerville special issue, We have also developed a building portfolio recovery model for earthquake hazard, which can output functionality state probabilities at any time t following an event for different building types, portfolio recovery time and recovery trajectory, temporal evolution of the spatial variation in recovery trajectory, and finally, the uncertainties associated with the recovery trajectory. In our ongoing effort, one of our ongoing effort is to work with other center teams to ensure building portfolio analysis is properly interfaced and connected to the analysis of other community networks and systems.
In this work, we are interested in analyzing how different building retrofit decisions might mitigate the effects of a disaster and improve community resilience. In particular, we're interested in allocating limited financial resources to retrofit building types in each zone of Centerville to specific code levels with respect to competing objectives, minimizing the direct economic loss and minimizing the total household dislocation. Additionally, we want to ensure that the retrofit policies that we consider take into account the resilience difference that often exists between different socioeconomic statuses. We add a constraint to the model to not exacerbate the existing disparity levels. Now, we do realize that community leaders don't have the authority to directly impose retrofit actions on privately owned buildings. However, for the sake of the study, we are assuming that direct or indirect incentives do exist and that they are effective. So given the baseline scenario in Centerville, we have a wide variety of building types, all at different code levels for both residential and non-residential structures. We estimated the ideal budget, which would be sufficient in order to be able to improve all buildings to their maximum code level. We, again, look at the same earthquake scenario, a 7.8 magnitude earthquake, and if we perform no retrofit, we expect a total economic loss of $856 million in Centerville, dislocating over 3,200 households. So we want to evaluate the retrofit policies and decisions that we can make under three different budget levels, low, medium, and high budget level that are given with respect to the ideal budget. So in particular, we look at what is known as the set of Pareto optimal solutions. Since this is a multiple objective problem, we don't have a single objective, a single solution, that would be an optimal objective, but we always have to look at trade-offs between different solutions. Along the vertical axis, we have the one objective, the direct economic loss, and on the horizontal axis, we have the household displacement. Our goal, of course, is to minimize both of these. The white region is known as the infeasible region because we simply don't have enough money to simultaneously reduce the economic loss and the household that are dislocated into that area. The gray region is known as the suboptimal region because all of these outcomes are possible, but we can do better, and that is represented by the blue line. The blue line is called the Pareto frontier. The solutions that produce these outcomes cannot be improved on at the current budget level, but they do represent trade-offs. For example, policy one at the top results in the highest economic loss, nearly $780 million, but the lowest household dislocation of about 2,500 households. These both represent significant improvements on the baseline policy. However, we have alternatives. We could also consider policy two. Policy two, for example, drops the expected economic loss by $45 million from policy one, but it does that at the expense of increasing the household dislocation. So while we do not intend to make decisions for the community leaders, we hope to quantify and support those decisions. The trade-off, for example, here between giving up $45 million in loss to keep 220 families in their homes, the question is that worth it? And we can't answer that question necessarily. The value of dislocation, of course, affects things like the tax base, economic growth, things that can be quantified by our friends in economics, but it also has a lot of elements that are hard to quantify. The quality of life, the stability of the family, and education. So while we can't answer these questions, the framework that we're providing, we hope, helps decision makers to pinpoint these issues. The competing nature within this problem itself is primarily based on how the money is allocated towards the residential structures versus the non-residential structures. The green line represents investment in residential structures, and the blue line is investment in non-residential. On the left side of the graph, we're investing more in residential, so we're reducing our dislocation, but we incur higher capital stock loss. And towards the right, we move our allocation towards non-residential, in which we have higher dislocation but lower capital stock loss. Now, if we increase our budget, the budget that we looked at previously is the blue curve here, the $52 million, the low budget. But if we increase our budget levels, we're able to reduce the infeasible space. So the red line represents the medium-sized budget, and then the green line represents the high level of the budget. When you increase the budget, you can change the shape of the Pareto frontier, and at the same time, the types of trade-offs that you're considering making. Additionally, the tool provides not only the estimates of what this Pareto frontier looks like, but it gives you specific details associated with zone level and building type granular interventions that should be taken to help inform good decision making.
Thank you, Paulo. So I'd like to present the work that was done on modeling the resilience of critical infrastructure systems and considering the role of network dependencies. And the paper focused on a unified methodology for modeling dependent infrastructure networks using a probabilistic procedure. And in terms of resilience, the focus was on recovery of the system as a function of time at the community scale. And the methodology simulated both direct physical damage as well as other damage caused by cascading effects due to dependencies, and then modeled the recovery level of the network functionality. So the methodology is general and can be applied to other systems. In this paper, we illustrate it with an example of water and electric power networks. So the dependency of the networks was simply modeled through an augmented adjacency table, a likelihood table, and a dependency table, and this is really more for conceptual purposes. But first note that there are two networks in the graphic there, the green network 1 and the blue network 2, and then the lines between them are illustrating dependencies. So this adjacency matrix then is constructed as shown below. So the connectivity between elements in network 1 and network 2 are in the green and the blue boxes on the diagonal of the matrix, and then dependencies between these two networks are shown on the non-diagonal terms, which are pink and orange on this diagram here. This is then further supplemented with a likelihood table that describes the likelihood of failure of a node given the failure of a node in another network. So we create the dependency there as well. And then we create a dependency table that is the product of this table with the adjacency or connectivity and the likelihood of failure. So the probabilistic procedure is based on Monte Carlo analysis, and just briefly, the 6 steps are to generate the network model and generate a hazard for the network area, and then direct physical damage is assessed through fragility curves, which has a probabilistic component. And then there is an iteration where we also include the cascading effects due to dependencies of one network on another. And then we assess the loss due to both direct and indirect losses. And there's a repair curve as well, data, to predict recovery time for the network functionality. And there's an iteration that goes on between these last steps to within a specified tolerance. So to try to explain this now with a water network and electric power network, this again is from Centerville. The water network is on the top and the electric power network is on the bottom on the right-hand side. And areas designated with A, B, and C are where we have commonality, where the water node depends on electric power node. So this is where your dependency is designated between the two systems. And you see the adjacency matrix below is showing the connectivity for the water network and the electric power network, and then their dependencies on each other. And in this simple example that we did, we have either a 0 for no dependency, independence between these two networks, and 1 for perfect dependency. If a electric power node fails, then the water node will fail as well. So we looked at these two cases, perfect independence and perfect dependence. And this is illustrated at the right based on the function of the water network. So given the physical damage that occurred and the direct and indirect damage at time zero, how can we predict these systems will recover, both for meeting the water demand and providing adequate pressure to meet that demand over time, based upon whether you consider the system alone, which is the blue line there, or when you consider dependency on another system. And you can see that the independent system recovers more rapidly than the dependent system, which intuitively should make sense. And even though the recovery begins around the same time, that dependency will affect the ability of the system to recover, and this is an attempt to quantify what that might be. So in concluding, we would just like to say that functionality is very important, and the delay in the recovery process with dependency can be quantified with this approach. It's very important in determining resilience that you consider the physical damage along with the operational aspects rather than considering them independently, and that the cascading failures can lead to increased recovery times that may not be accounted for if that's not included. And this method is considered modular in that it can be applied to any network and type of dependency. Thank you.
So I'd like to talk today about the differences between spatial and aspatial and non-spatial CG models, because as it turns out, most natural disasters have a disparate impact on a region. So what we're arguing is that you may have to build a spatial model to capture the unique characteristics or varying characteristics of a natural disaster. So what we've done for Shelby County is we built two models. One is just a one-region Shelby model, and then one is with subregions, and we have 8 regions. And the 8-region model is much more complicated and costly to produce, but we believe that it can better estimate the distributional impacts of a natural disaster. So I'm going to show you how we've done that. So here is Shelby County, and it's conveniently broken up into 8 different PUMA regions. Each PUMA region has to have at least 100,000 people, and this has to do with the U.S. Census and how they organize data. So the little thin blue lines represent the 8 different PUMA regions, and Memphis is actually located in 3201, 3202, and 3203. So the majority of the population is, in fact, in these 3 regions. But as we know, an earthquake can impact these different PUMA regions very differently. So what we've done is we built 2 models. The spatial model has employment centers in each one of these 8 PUMA regions. And the employment centers, given the type of data we're organizing, is 3 sectors: goods, trades, and other. And then we also have 3 different household groups, housing groups in each 5 housing groups and 3 housing services, but the household groups are 5 household groups per PUMA region, so there's 40 household groups. And again, they're spread out all over the county. And so what's the case is, if someone lives in 3201 as an example, they could reside there, but they may be employed in 3204 or 3205. So what we have is the data. We know where people live and where people work. So we have a nice grid of commuting patterns in this model. And the non-spatial, or aspatial model ignores all these PUMA regions and just has 3 commercial sectors for the entire county and just 5 household groups. So instead of having 40 household groups in the spatial model, in an aspatial model, we only have 5 household groups. So we really aggregate things up. So these 2 models actually behave very differently. And so the idea of economic analysis really is dependent upon something called substitution, is that when different PUMA regions are impacted, they're impacted in a different way to where prices move differently. So where one PUMA region may be impacted severely, another PUMA region may not be impacted as much at all. So what we'll find is relative prices will rise in the area that was damaged, and people who live in a damaged area may end up shopping more in the non-damaged area. So what you'll find is, in a spatial model, you're going to have all this substitution going on, which can actually minimize the impact of the disaster. When you have a spatial model, there's limited substitution that can occur because all the commercial sectors are just grouped into one. So So the disaster just impacts these three sectors, and there's very little substitution that can go on. So what you find is that the output or the economic losses when we shock the aspatial and spatial models identically, the economic losses are larger in the aspatial model because no substitution can occur. So as an example, employment falls by 37,000 workers in the aspatial model and 35,000 in the spatial model. So what we're arguing is if you used an aspatial model to model a disaster, you're going to overestimate the economic impacts. With a spatial model, you get all this substitution going on, and in fact, the losses are somewhat less. Not a lot, but in terms of recovery processes, it can be important. Here is, we've looked at household income, and this is actually really demonstrates the difference between this aspatial and non-spatial and the spatial models. Is that, let me go back actually. For economic losses in terms of real household income, the aspatial model predicted a $1 billion loss in real household income, where the spatial model predicted only a $681 million loss in household income. And again, this is shocking the economy and not examining any types of recovery processes, no infusion of resources. We're just looking at the prompt effects of the disaster. So focusing on a difference in real household income, what we've done here is we've looked at the distribution of household income losses. Now, in the non-spatial model, all we have is 5 household groups. And we can see that HH1, families that make less than $10,000 a year, lose $10.3 million in household income, or 3%. Now, in the spatial model, what we've done is we've added up all these different housing groups from the 8 PUMA regions. So we have 8 HH1s in each of the 8 PUMA regions. So we add up the economic losses of HH1, or the lower income households, across the 8 PUMA regions. And what's interesting to show is that the economic losses for HH1 are larger when you spatialize all of the household groups, but in HH2 through HH5, the losses are smaller. So what we're saying is these spatial models are really important in understanding what happens in when a natural disaster occurs. What also a spatial model can describe is, in this last table, is that we can estimate the disparate effects of the natural disaster. So we can see that in terms of domestic supply, Region D loses the most amount of economic activity at 19.3%, and Region G is the smallest fall of 11.3%, and that's consistent with how much damage occurred in these different PUMA regions. And because of all the modeling we can do, when Nayu ran these shocks, she damaged each individual building in Shelby County. We then aggregated up these buildings into our different sectors, and with the spatial model, you can see a wide variation in the damage and the economic losses. So then what we try to do is figure out what type of natural disaster would permit you to build an aspatial model. And we're still debating that in our econ group. And we haven't come to one mind on that. But, oops, wrong way. Oh, I guess I don't have my last page. Okay. I had a conclusion, but I guess it's not here, but that's all right. So, in the conclusion, you can imagine, if it was up there, Sammy Zaron, I don't know if Sammy's here yet. He's teaching a class right now. Sammy argues that Katrina had pretty uniform impacts in the New Orleans area for the following reason. Downtown was up on a bluff, so the flooding was not as bad. But the rest of New Orleans got severely damaged, so it was he maintains a homogeneous level of damages in New Orleans. Now, we haven't looked at the data. That's his hypothesis. So if we have a homogeneous impact of damages across the region, it might be all right to build a aspatial model because there's not much variation. But I argue that the vast majority of natural disasters have very disparate impacts in the region. I think you have to build a spatial model. So, but we're still working on that. We're also trying to determine what type of natural disaster would actually, just artificial one, would produce a totally homogeneous impact across regions and then allow us to build an aspatial model, but we're not there yet.
So in case you're just wondering what hindcasting is, It's a systematic process to check the accuracy of our models using a past event. And for Joplin, we'll do this both for individual buildings and components and aggregate those into system levels. And this will be done at points in time to validate damage modeling, loss estimation, population dislocation, and then functionality and recovering over time. So about Joplin, Missouri, it has about 35 square miles. Its census population is about 50,000, but because many people come into this community from the surrounding area, it can swell to 3 or 4 times that level in the daytime. They have about 23,000 housing units, and the median value of these units of the houses are about $103,000. So into this community on May 22nd, 2011, the Joplin tornado occurred. It reached peaked EF5 intensities. It resulted in 161 fatalities. Over 1,000 people were injured. And it was the most expensive tornado in U.S. history to date, with losses at $2.8 billion. So it touched down about 5:34 on a Sunday, and it stayed on the ground for 22 miles and 15 minutes. 6 miles of the path were through the city of Joplin. Based on the damage, it was rated to be enhanced Fujita scale EF5 tornado with maximum wind speeds over 200 miles an hour. This ended up destroying about 1/3 of the city's buildings, and 40% of the city's population was affected. With the fatalities, this was considered the single deadliest tornado on record when you look at tornadoes, hurricanes, and earthquakes. And the official warning time to the community was 17 minutes. The national average is 14 minutes. And you can just see in the diagram here below, the red line is indicating EF4, that very dark line, EF4 and 5, I believe, and then the shades go out showing the less intense wind speeds as you get away from the center. So NIST, with the fatalities and the damage that occurred, deployed an investigation team and conducted a technical investigation. The objective was to determine the tornado hazard characteristics and associated wind fields, the performance of the buildings, including shelters and safe areas, and the performance of lifelines as they supported these buildings, the pattern, location, and cause of fatality and injuries, and associated emergency communications and public response. And finally, areas and current codes and standards that might warrant revision. So the report actually had 16 recommendations and a number of findings. There's not enough time today to go through this, but here are 4 findings that set the stage for the work that you'll see in the following slides. 40% of the fatalities and as much as 90% of the tornado damage area were associated with EF3 or lower wind speeds, and that's about 160 miles an hour. Of the buildings damaged, 7,400 are residential and 550 were non-residential. There was engineered structure, St. John's Regional Medical Center. It had the building envelope damaged. There was very little damage to the structural frame, but it ended up losing all its functionality due to the damage to the building envelope, and ended up being declared a loss. All the utilities, water, gas, and power, were lost in the area, were most damaged, and they had their service restored to critical buildings within 24 hours. And it was a great example of how utilities can work with the local community to prioritize the type of restoration that's needed. So with that, I'm going to turn this over to Professor Vandelent.
So modern electrical power distribution is versatile in providing service coverage, which makes it actually much more difficult to model. One of the key aspects of the center is importing algorithms and methodologies when they fit the needs of the analysis. But there is substantial new development also underway. The results of a study from approximately 15 years ago at Los Alamos Labs was applied to use weighted cellular automated to identify electrical service coverage areas. This figure isolates a prediction of just the pole and transmission line damage for the EF2 rated region. So what this means is anything inside this path that you see, the black inside, is EF3, 4, and 5, but it's not shown here. So for the full electrical power network prediction, a total of 113 transmission towers and about 3,740 distribution poles would be badly damaged. So how does this compare with what was observed following the tornado in 2011? That was 135 transmission towers and 3,850 poles that were badly damaged or collapsed, or destroyed, I should say. Modeling all the physical components within a community's infrastructure is a significant task, as anyone knows that set up a spatial earthquake model, and certainly they can attest to that. However, unlike earthquake fragilities, building fragilities for tornado loading are quite scarce. So one of the joint efforts for the Buildings task team and the Joplin Hindcast team was to develop a portfolio of buildings representative of a typical community or a city. It was decided that a minimal portfolio of 19 buildings would be used and essentially provide analysts the ability to differentiate between critical attributes affected by wind load in a tornado. Obviously, a community has hundreds of building types, but the key here is not to model each building individually, but have a fragility for damage and recovery of functionality that's accurate enough to interact with other physical and non-physical components in a community level model. The fragilities range from 6 different residential structure fragilities to heavy industrial facilities to schools and community centers. A typical community can have tens of thousands or more buildings, making assigning fragilities a formidable task. In addition, it's critical to be consistent in the assignment of these or any functions. Although not presented in detail here, the center has adopted the GEM taxonomy, which is being extended from earthquakes to other hazards. Here we see a snapshot of the tornado taxonomy, which begins with level 1 attributes such as enclosure classification, height, roof shape, and other building attributes that affect wind loading intensity. Then level 2 attributes provide better information upon which to characterize the building and assign fragilities. For vertical load path continuity, this could, for example, be a full roof to foundation load path. Once the 19 fragilities are assigned to the buildings in Joplin, the probability of each building in a damage state can then be determined. For example, in damage state 1 that you see, damage state 2, 3, and then a damage state 4. The computation is performed using an algorithm to convert the building to a point, and then it's converted back to its original geometry in GIS, as shown here for damage state 4. Then for a multi-sector validation of buildings and the electrical power network, both sectors can be combined. This image, which shows all the buildings in Joplin color-coded, depending on which of the 19 fragilities was assigned to them, and then also it shows the lines, which are showing the power transmission and distribution networks. Here we see the CA algorithm with both sectors represented. This work is ongoing, and at this point, damage to buildings, the power network, and their functionality interaction can be modeled. A 4-step probabilistic post-disaster functionality methodology has been developed to be applicable to any building type and hazard. This methodology integrates performance-based engineering concepts within the context of community resilience for buildings and combines them with repair and functionality analyses to allow quantification of building functionality through a series of Monte Carlo simulations. This methodology is illustrated through the example of 3 building types identified in the Joplin community building stock, namely a school, a heavy industrial facility, and a strip mall, with the assumption that these are in building damage state 3, or what we call extensive damage. The intrinsic functionality fragilities, accounting for only construction and cleanup time, as well as the semi-intrinsic functionality fragilities, accounting for additional external factors such as time to obtain financing and permits are generated to quantify the probability of the building's post-disaster functionality. It can be observed that post-disaster functionality levels differ for the three building types depending on their construction details as well as their occupancy type. In addition to the hazard intensity, the continuity of businesses following a disaster are affected by factors internal to the businesses, such as decisions on business operation, capital investments and cash flow, supplier and labor availability, and customer demand. Passive business characteristics, such as employment and line of business, also affect the impact and recovery. External factors affecting business interruption and continuity include utility lifelines, transportation networks, and telecommunication, to name a few. Policy interventions such as insurance and government assistance also affect the short to long-term recovery outcomes. In order to estimate the probability of business closure 3 months after the event, the interdependency of physical structural damage and business characteristics is modeled. And I see we're using a Mac. This was developed on a PC, so I see we have an equation problem, but we can get you that equation if you're interested. So, first, the expected damage is estimated by calculating the sum of severity of the damage at each damage state, weighted by the probability of each of the damage states. Then business characteristics such as employment size, franchise status, and sectors including manufacturing, construction, and retail are considered. The map at the top shows the probability of business closure at each business location. As would be expected, the business closure tends to increase as the tornado intensity increases. No businesses were predicted to have closed in the EF1 region of the tornado. About 6% closed in EF2, 77% in EF3, and above 97% of the businesses closed in the EF4 and EF5 regions. The total jobs affected were 945, and total annual sales value affected is predicted to have reached over 176 million. Although just under development, a computable generalized equilibrium model similar to the one you heard about for Centerville will provide a measurement of the economic impact the tornado had on Joplin. Predictive models for each year will be developed to determine how well the forecast predicts changes to the local economy. Population data from the Census Bureau was used to determine the spatial variance and social vulnerability. The social vulnerability perspective focuses on the social factors and processes that generate vulnerability in terms of an individual's or group's capacity to anticipate, cope, resist, and recover from the impacts of hazards. Social vulnerability is not uniformly or randomly distributed within our communities, and therefore it's important to know where socially vulnerable populations are located. Previous research has used county-level and census tract data to explore this question. The INCOR process is using census block groups to process or provide a finer resolution, which is important for hazards such as tornadoes, which impact a much smaller geographic region. This slide compares the resolution provided by census tracts and census block groups for Joplin, Missouri. The areas shaded in orange and red have a higher index value of social vulnerability. This slide provides an example of why using a finer resolution such as block groups leads to more accurate assessments of vulnerability. In the case of the 2011 Joplin tornado, the fact that the tornado path was through areas with higher population density helps to highlight one of the shortcomings of census tract data. In general, the larger resolution assumes lower levels of population density and leads to an overall undercount of the population. The undercount is even greater for socially vulnerable populations, which were more highly concentrated in block groups impacted by the tornado.
So today we're going to talk a little bit about an update on our Hurricane Matthew longitudinal study for Lumberton, North Carolina. So this is one of our field studies within the center. And I'm going to first give a little bit of an overview of the event itself before I talk about the study goals and objectives for this return visit. So Hurricane Matthew hit as a Category 1 in October of 2016 and impacted the state of North Carolina in both the coastal and the inland areas quite a bit. Over 15 inches of rain fell in some parts of this state, and flooding was exacerbated by the pre-existing conditions. There had been a lot of rain during the month of September, so grounds were heavily saturated and ripe for flooding. In Robeson County, over 5,000 people were placed in shelters and in temporary housing by FEMA, and all 42 schools serving 24,000 children were closed for 3 weeks in this county. So here you see the location of Robeson County in the state of North Carolina, and within the black boundary is the city of Lumberton, and this is our study site. And below our study area and also the inundation from the flooding, as well as our selected school attendance zone, which I'll talk about in just a moment. So you see Lumberton is quite inland from the coast, but still had significant impacts from the hurricane. Lumberton has a population of about 21,000 people and is highly diverse in terms of its racial and ethnic composition. You see in this pie chart that the population is largely comprised of 3 groups: a Native American population, mostly Lumbee Indians, Black population, and a white population, as well as a fairly good-sized Hispanic population in this city. So while we're continuing the review of Lumberton and the flood impacts, we wanted to show you a simulation of the flooding within Lumberton and give you an idea of some of the additional work that's happening within the center. So while we usually talk mostly about our field work when we do our presentations, there's an important and extensive amount of background work happening related to the hazard modeling itself and some of the other engineering analyses. So this simulation was conducted by Omar Nafal at Colorado State University, and you see the magenta boundary of Lumberton. And the darker colors of blue in this simulation reflect deeper waters in line with the topography of the city. So 2 major streams enter Lumberton, and in the 600,000 element model with an unsteady flow simulation, we have these 2 main streams coming in. One with upstream data is from the USGS, and then the downstream data is just based on gravity flow. So the measured flow rate for these two streams comes in at 7,000 cubic feet per second, because we have one that's measured, one that we're assuming, and then the measured flow rate for this city is 14,000 cubic feet per second. So as you can see, this model accurately predicts where the water has come into the city over the interstate and around the railroad track, just as it happened in 2016. And here you see from some satellite imagery the pictures that represent that overtopping of the interstate and coming in through the railroad. As an ongoing acknowledgement of the importance of sharing some common terms and making sure that we talk about the meanings of these terms, we define here what we mean by a longitudinal study. So this is the methodological approach that we're taking for this particular field study. And it allows the same cases to be observed over time to track changes, both positive and negative. And in the case of this event, and in most hazard events, it's really important, if we want to understand recovery, that we do this return to the same place, studying the same cases over multiple time points in order to be able to record observations that get us a better understanding of the recovery. So our timeline is that the event hits in October 2016. We do our Wave 1 data collection in November of 2016, and we followed up with our Wave 2 data collection in January of 2018, and we expect to return as well.
So first, let's take a look at single-family housing samples. This sample here, we We recorded as having been gutted in 2016 when we visited it, and you can see the piles of trash in front of this structure, and we recorded this as a damaged state too. So this damaged state is on a category, it ranges from 0 to 4, where 0 would be no damage and 4 would be complete damage. When we returned in 2018, we were actually able to talk to the residents and confirm that this housing unit was occupied and had been fully repaired. So that was wonderful. Unfortunately, not all of our housing samples had happy endings. Here, both of these samples that you can see in the picture or both of these units you can see in the picture were our housing samples. Both units had been gutted and recorded as damaged state 2 when we first visited them. When we returned, the left was recorded as abandoned. It appeared to be abandoned, whereas the right was no longer there, and so we marked it as being demolished. This starts to show the variability in recovery trajectories when we control for damage level and housing type. But let's look at another housing type, multifamily housing. We visited these apartment buildings in 2016. They had been gutted and again recorded as damaged state 2. When we returned in 2018, they were unoccupied and still needing repair. That initial gutting work had been done, but minimal progress towards reconstruction had been made. And our last type of housing sample that we'll look at is public housing. So this is one public housing facility that we visited. These had also been gutted and recorded as damaged state 2. When we returned in 2018, they were unoccupied and still needing repair. And this was largely what we observed across that public housing complex. So let's take a look at businesses. Here. Now, we did not survey businesses in Wave 1, as you heard earlier. When we visited them in Wave 2, we asked them about the repairs they had to do, the damage that they experienced, and we did an analogous classification of 4 damage levels based on that information. So this building that you see was classified as a damage state 4. We also asked the owner or the manager that we spoke with what their perceived status in recovery was, and so this business owner indicated that they were still in operation but would never recover from the impacts of the flooding. To leave you on a happy note, another business sample recorded as damage state 4 indicated that they had mostly recovered when we talked to them in January of 2018.
So with our sampling, we began with the flood inundation area in Lumberton. And from here, we selected highly impacted schools within this inundation area. We then draw our housing sample from the catchment area for these different school zones. And finally, in Wave 2, we draw a business sample using the combination of the housing sample, the school zones that are highly impacted, and the inundation area. And in both cases, you see our sample points on this map on the right-hand side. You'll notice that for both housing and business, we select some businesses and housing that are outside of the inundation area in order to understand the broader impacts of the hurricane. So while we're looking at physical damage directly from the flooding, we're also taking into account a broader set of impacts on this community. So in order to look at interdependencies through data collection, we're going to talk about how some of these different sectors are linked, and then how we went about developing methodology that would help us assess these linkages. So here we are looking primarily at the residential and business sector and trying to understand how the recovery of households and businesses are linked. So residents need work in order to stay in their community. They need a job and a place of employment, and the businesses need employees. So our question to households is, to what extent did the members of the household miss work due to Hurricane Matthew? And if so, how much? So we're trying to establish the degree of the impact of the event on their ability to get to their employment. And then we wanted to know what industry they were working in. So this would allow us to start to make some linkages across our business survey as well as our housing survey. Again, we're looking at the connection and the access between these services So here we look at education sector and residential sector, as well as a broader set of community services. And we want to know a series of things that may delay a household in returning. So now we're getting beyond just the employment, and we're thinking about access. What are the access to services? What about the child's school, place of school enrollment, and a closure or a change of that school? And then the educational recovery of the children. So we ask this of households in order to make linkages between the qualitative data that we're collecting from our school representatives and try to understand how the timing of these pieces and the decisions that are being made at the school level are having an impact on the housing recovery, and the opposite way, on the decisions made by households having an impact on school recovery. And finally, we look at the dependence of the physical recovery of these housing units and business establishments on the restoration of the supporting infrastructure that they need. And we wanted to know in both cases about disruption, so the length of disruption, the severity, and which particular infrastructure elements were disrupted for each housing and business. And this helps us to establish a better overall recovery timeline. So what we found in many cases is that the coming back on of particular infrastructure services had everything to do with when the business returned to operational status. So while electricity may have come back very early, the lack of water delayed businesses quite a bit. And for many of them, they were entirely dependent on their physical location to operate.
So in conclusion, as a result of the Wave 2 data collection, we are able to investigate differences between housing damage states in Wave 1 and Wave 2 to improve field study methodology, as well as test out new technologies and use new equipment in the field. We're able to support the ongoing development of recovery models for housing, businesses, and for schools, as well as inform the structure of an integrated community recovery model using those interdependency-based questions. As you can see in our data, and as we learned, many households, housing units, businesses, and other community sectors are in the early stages of recovery. Some types of federal assistance had not arrived to Lumberton to be distributed to households, among other places, or arrived to many of the schools in Lumberton as of January of this year. We are planning to return for a Wave 3 trip and hoping to do a Wave 4 trip as well. And so we will be reaching out to members within the COE team for your help. The Wave 1 report is to be released soon, so please check the COE website, resilience.coloradostate.edu, later this summer for it. Thank you so much for your attention. Thank you to the so many people who contributed to the development of this work and these slides.